Welcome to Season 10 of the Prosthetics and Orthotics Podcast. This is where we chat with experts in the field, patients who use these devices, physical therapists, and the vendors who make it all happen. Our goal? To share stories, tips, and insights that ultimately help our patients get the best possible outcomes. Tune in and join the conversation. We are thrilled you are here and hope it is the highlight of your day.
Hello, everyone. My name is Joris Peels, and this is another edition of the Prosthetics and Orthotics Podcast with Brent Wright. How you doing, Brent?
Hey, Joris. I'm doing well. I tell you what, we had so much content come out from AOPA. It's like I'm still buried in that, you know?
Yeah, totally, man. That was crazy how much you recorded when you were there, man. I really missed being there. That's first off. I really need to go, and it was a lot in a very short time. But then I missed the regular cadence of talking to you every week and doing this every week. So it's kind of like a double kind of thing. So on the one hand, it was amazing to have so much content, and that whole random thing where just random people would come and just keep coming to join us was completely crazy and a lot of fun. So I enjoyed it, but yeah, I do miss our regular episodes, I'll say.
Yeah. Well, we'll get this one out, and I'm really excited about this one. But I did want to just share, Dwan Scott put on an amazing conference, the CDFAM conference in Brooklyn, and it was really great.
Yeah,
it's amazing how far in really, I say a relatively short amount of time, but like the computational design, machine learning, AI, all that stuff. And what was neat is a lot of the people kind of defined what was going on. What is AI? What is machine learning? Do we believe in AI? What are we doing? And the bottom line that I took away from it is there's still a human aspect to it, right? It's what can the humans input to get results that you want. But for really from anything, there was a that started off doing computational design, but they started with like jewelry with it looks like leaf veins, and so they had this algorithm that creates these leaf veins that are uber realistic, and each piece is different. But then a surgeon saw what they were doing and said, "Hey, that looks like human veins." And so now they still do some of the art stuff, but now they're using these algorithms to print tissues and vascularize these systems. And it's going pretty well. They're trying to miniaturize, but it's just amazing where that goes.
Okay, that's super cool, man. And I know I've been hearing good things about the conference from other people. But who's it for? Is it really for people who are really deep into this 3D printing, DFAM design stuff, or what kind of people should go to that conference next year?
Yeah, so I can imagine it's kind of like, the early days of AMUG, where it was like, these are the people that are down in the trenches, and you actually have access to them to talk with them at lunch breaks and, the breaks and such. It's a very small, intimate group. But these are the people that are literally writing the software, creating these ideas. They're architects, some in healthcare, the shoe space. So I would say for the time being, if you're interested in that stuff, you may get something out of it, but it gets into the weeds pretty quick. And so I could definitely see somebody that's, not even really 3D printing or doing much of anything on the software side, really getting lost in a hurry, and it wouldn't be very beneficial. But for those that are actually in it, I think it will open your eyes, but then also connect you to people that are doing really great things.
Okay, and if I'm working software in any kind of way, if I'm day-to-day in front of a CAD doing additive, or if I'm making a software package, I should totally 100% be there, right?
100%. Yeah. Especially if you're wanting to look at how are you going to automate? How are you going to train things? And this is the first conference. And I wanted to do a post about this, but I didn't know how to put it all together. That's kind of funny. Like things that you see at CDFAM, and it's like people taking notes and coding their software program at the same time. They're like in the audience, and then I looked over and there's a guy playing chess and listening. So this is not like the normal conference. These are like uber smart people. Like I was definitely not among, among that.
Did you feel out of your depth?
Yeah.
We were like, oh my
I
God.
definitely, it was an outkicking of the coverage on my side of things, but I got to talk to a lot of cool people.
Okay, that's good. Did you get to speak or not?
I did, yeah. So I got to share what we've got going on with Life Enabled and some of the automation that we're trying to do to bring prostheses or access to prostheses worldwide and really lower the barrier to entry to get prostheses on people where software is going to be an issue and then upskilling on the software will be an issue. So I was really excited to be able to share that.
Okay, that's super cool. And did you get a lot of like feedback from people? Were a lot of people interested in that, or was it too specific for them, or did they really like the application?
They really liked the application, and I got to talk to, yes, a bunch of people afterwards. And in fact, I'm going to probably be working with some people doing some finite element analysis using some other structures. So I was always curious, and I don't know if you've had them on, the guys from Spherine.
No.
Oh my goodness, they've developed this structure that's a circular structure it's made more for the powder bed fusion side of things, which might be appropriate for today, but it's stiff in all directions. So like a truly isotropic structure that is developed. And so you'll have to, I'll put it in the show notes too, but it's called Spherine.
Okay.
And they just had integration into Rhino. They just had integration into Entopology. But it's not only stiff, but it can also be used on the heat exchanger side. And they've just made it very easy to make it. And you can do different densities, different wall thicknesses. Like there's a lot of great features that go along with it. So I highly suggest you check it out. But I was just doing some exercises on my part with it. And literally it's up to a 70% weight savings.
Wow. That's amazing. And what are these guys? They're selling the software to make a specific geometry? Is that what they're selling? Or?
Yeah, so it's a software to create this specific geometry within a volume. But this is like kind of like dumb me. Like it's almost like a plugin, I guess you would say. But I'm definitely undercomplicating it. It's more than a plugin because there's a lot of other things that are going on. But it allows you to get this structure and put it onto your devices.
Okay. Interesting. That could be interesting for us as well. That's cool, man. I'm glad you went to that. And yeah, super cool. I need to get, I feel that's also not exactly my part of the fence either. So I always feel like, I should go, but then I don't go. I don't know. We should go at one point.
I did get to speak with John from 3dprint.com.
Cool, man.
Yeah. So I hadn't met him in person. He goes, "Hey, man." And so we had I didn't realize he was from New York and he had come down.
Oh, that's cool.
Yeah. So that was kind of fun to.
Awesome. I'm glad you met him, dude.
Yeah. So that was cool. So we have a long-suffering guest, though.
We have a guest? Oh my God, the poor guest. Who's our long-suffering guest?
So this one's going to be an interesting one. So this is Luke Rodgers. He is the CEO of a newly formed company called Loomis Polymers. And we have talked about PK 5000 before. And he is the brainchild behind it. And so I think we're going to have a lot of fun.
Thanks for having me, Brent. Appreciate it.
That's super cool. Welcome to the show, Luke.
Thank you.
So, okay, Brent is the number one fanboy worldwide of this PK 5000 stuff. And just a little bit of like a background, or maybe more generally, before Luke can take us a bit further, I would think we've always struggled in powder bed fusion, particularly, but also all other additive manufacturing, 3D printing technologies to really make really strong, really kind of resilient materials that stand up to the wear and tear of the outside world. The stuff that is easy to stick together is not the stuff that is then easily stuck together forever, kind of. That's always been our problem. And so one of the people have been going all sorts of ways with that. One thing is to fill your materials. One other way is to put lots of additives in them. Another way is to use a relatively strong kind of base material, or to do combinations of those things. And there have been a lot of work around PEC, another kind of polyether ketone, ether ketone type materials, that kind of PEK family. It's very difficult to print and very expensive to print, but really high performance. And there's been a lot of work on polyamide, like nylon type, PPA type materials, so high performance type of versions of the polyamides we all know. And then there's all of a sudden there's this PK 5000. So tell us a little bit about this PK 5000, this material.
Yeah, thanks for letting me talk about it today. The PK5000 material, and when people think about polyketones in general, they do tend to go right towards the aromatic type that you were just mentioning. So the polyether ether ketones, the polyether ketone ketones, those are the high temperature, high rigidity, expensive polymers that most people think of when they think of polyketones. PK5000 is actually based on an aliphatic polyketone, so it's highly flexible backbone, which means it has a lower melting temperature and is much cheaper to make. So it's relatively inexpensive compared to the traditional polyketones and is on par with the polyamides that you would be using in your typical SLS systems today. In general, polyketone that are aliphatic has some really interesting physical properties. When you look at the overall resistances to chemical resistance, the overall toughness of polyketones, those are retained in the aliphatic materials. And you mentioned, one piece of the puzzle, and when we look at actual utilization of additive manufacturing parts in end-use applications, it's been really hard for the additive manufacturing industry to put, shall I say, a relative data together to be able to compare materials to really understand what their actual damage tolerance is. So a lot of us have historically looked at trying to increase just the impact strength of polymers. And impact strength is great for comparing how parts are going to fail on a hard impact or if they've got a flaw in them. And it's an important part of actually determining if your part can survive the end use application. But one thing that additive has done a poor job in really comparing is the resilience of materials, and it's a little bit harder materials property concept to wrap your head around. But if you look at the stress strain curves of any plastic, the resilience is really the area under the tensile stress strain curve up to the actual elastic limit of the polymer. So when most people look at data sheets, they look at what's the yield strength, what's the impact strength, but we really need to understand what the curves look like and start pulling out what exactly is our elastic limit strain and our elastic limit tensile stresses to be able to understand what type of damage tolerance these parts can take. And if you were to compare those curves, and we'll put some in the notes of the show, if you look at PA11 and PA12, their elastic limit is between 3 and 4% elongation or strain, where the polyketone product, the elastic limit for elongation is around 8 to 10%. So there's a lot more area under the curve, a lot more overall energy that can be absorbed by polyketone. And it's a really hard concept to wrap our head around, but it's quite evident when you look at the stress strain curves.
I've always looked at this personally, and this is my little mental model for me, right? Okay. So I don't know, please correct me if I'm wrong, but this is how I've tried to understand it. That impact strength is kind of like some really sharp object hitting a bridge and breaking it, right? But what you're sort of describing is really like everyday cars, driving up and down that bridge, and that bridge kind of responding in line to all the stresses of these cars, putting weight on, putting pressure on, and going up and down that bridge and withstanding that pressure day in, day out. And that to me is the kind of thing that we always like focus on, this that high-end impact strength, but really is what can that bridge, is the little mental model in my head, can that thing sustain day to day, just kind of like continuous service temperature, where you're like, no, it's not about when the thing melts or when it starts to melt, but it's about where can we operate this polymer, in a day-to-day kind of conditions, that it kind of will keep its properties. Is that kind of the right way? Am I at least in the right ballpark, thinking about it like this way?
You're absolutely right. That's a great way of describing resilience. It's how much load that part can take continuously without losing its actual shape of the part. So polyketone can take a very large amount of deformation and load carrying capability before it starts to deform. So there's a lot of energy under that curve that it can continue to take and have all those repeated uses before it actually deflects, versus like you said, the impact strength or the impact toughness is really about catastrophic failure. Like I get hit by a baseball or something like that. Can that part take that impact? Versus what's the repeated utilization of that part when I'm running or using it to pick up something.
And to me, always, like, if we see what we have a problem in powder bed fusion, particularly And for polymer, we have a problem with maintaining Young's modules, maintaining kind of our performance and elasticity and all these kind of properties on the long term in the part. And we also have a problem with fatigue, strength, and also a problem with like kind of impact, generally strength, generally. So you're kind of saying that, on of these problems, we solve very particular ones that are kind of really, really helpful if you're trying to make something that's like a kind of a baseball glove, something that you're going to use every day and going to kind of put under strain every day, right?
Yeah, so that actually refers to something that's very similar to resilience, which is recoverable work. So recoverable work is typically where a part is fatigued to the actual stress that it's going to be utilized at. Then what is the energy under the curve of that fatigued state? And we'll include some notes about the typical polyketone recoverable works in the notes as well. And that's really where that fatigue limit, where does the actual part go when it gets to fatigue, and how much work can that part do at that fatigue limit? That's recoverable work, which is also a really important part that we haven't covered well in the additive industry.
So this is interesting, and yours, you may speak to this too, but Luke, I'm just kind of curious. I mean, so, a lot of people are focused on the polyamides, PA11, PA12, and even like the polypropylene. But it's like, to me, while those perform, and they perform well for a lot of things, I mean, there's a ton of people out on these with the prostheses that are wearing prostheses and such, like if you bring it to my world. But like, it really wasn't until I heard about some of this other stuff that is important in plastics. It's I don't want to say the industry's it's not talking about this stuff, but it's the polyamides and the polypropylenes, they don't have these features. And so you don't necessarily talk about them. So it's not a story to tell, essentially, within, the current state of OEMs and powder bed fusion. Is that a fair statement?
I would say that all polymers have these properties, and any good engineer can design around the properties for a given problem statement. I think what polyketone, the PK5000 product, does is it gives you better resilience, better recoverable work to allow for more flexibility of your guys' designs, and a lot more application spaces that maybe couldn't have historically been done in a single article build. You can incorporate into a PK5000 build because of the added resilience and added recoverable work of these types of products.
Okay, so what you're saying is that, yes, you can make pretty much, you can engineer around some of the shortcomings, I guess you would say, of any of the powders. You make it thicker, thinner, or what have you. But sometimes it may be looking for a different tool as well, and what tool is going to make the most sense for your particular product.
Absolutely. And people are going to sell what they've historically had, right? So if it's not an option on your additive platform historically, you can't sell for it. But as we've seen with Ultim 9085 in the FDM market, once that tool gets out there, it starts to get adoption for its unique physical and chemical properties.
Yeah, and so talk to us a little bit more about this material. All right, we got aromatic, right? Which means they smell nice, right? And aliphatic. So aromatic, they have something with rings. Could you explain a little bit that difference, a little bit, because between the stuff that people know, and you already alluded to like the difference a little bit with like the regular peak and PEC. And if you're not familiar with them, if you're listening, that's kind of the material everybody asks for. If they're looking for high material, high performance, it has some really interesting properties. Peak is inherently flame retardant, has a really high surface temperature, but it's really difficult to use. It's really difficult to crystallize. And I think on that crystallization front, which is really the problem if you're printing these materials or trying to reuse them, that kind of thing, that's a huge problem. That keeps people from making big parts. It keeps people from industrializing this because it's super expensive in the first place. And then you try to make your part and you end up with like kind of like brown sugar kind of thing. Where does this aliphatic aromatic stuff, where does that feature? And what are the big differences between like the peaks we all know and hate? Oh, sorry.
Good question. So when you think of just aromatic versus aliphatic, all that really means is that aromatics have aromatic backbones that are much more rigid and resist deflection of the actual polymer backbone, versus the aliphatics have a very flexible backbone. So that's the easiest way to think about it, just visually in your mind when you think about chemistry. And those very rigid backbones have high TGs, high melting points versus the ones that have more flexibility, it's easier for that polymer to start bending and moving. So it then really has a lower modulus, it has a lower melting temperature compared to the aromatic type polymer. Same thing happens in aromatic polyamides. So there's aromatic polyamides that are very high temperature, like PPAs, versus the traditional long chain polyamides that we're used to working with. Same thing happens on both of those types of chemistries versus whether it's a polyamide or a polyketone. How rigid that backbone is dependent on the monomers you use to make the polymer.
Okay. And let's talk to us a bit about where do you see this playing a role? I mean, because on the one hand, it should be easier to process. And on the other hand, it's much cheaper, right? And on the other hand, we probably don't need like 420 degree muzzle temperature, stuff like that. It's the processing temperature also means that we can use different printers for this, right?
Yeah, so our polyketone is a powder-based product, right? So it's available in powder bed fusion processes that can be inerted. It doesn't require a nitrogen environment to be printed. So it can be utilized at standard utilization temperatures. So it's got very similar melting temperatures to PA12 and PA11. So it's commonly available in traditional SLS platforms. It doesn't require a high temperature SLS platform to run in, although you can run it in them as well. So that lower melting temperature does allow for it to be utilized in all different kinds of fielded systems today. And I would also say that in general, when people switch to polyketone and get it onto their printers, because of those tangible feel of the parts that we just talked about and the resilience and recoverable work with these types of parts, most of our customers that switch don't switch their printer back to the other materials they were using. They usually stay with the polyketone product because it is different once you get your hands on it. It's hard to understand from a data sheet, but when you feel the resilience of the parts, you can tell that it's different.
Okay, and then talk to us about the economics of this. Because, okay, if you're looking at Peak and Ultem and all those kind of things that people use instead of this, or partially instead of this, I guess, you're talking about materials that are also quite brittle, but also that they have very poor refresh rates. So in a powder bed fusion system, you may, if you're using Ultem or other materials, not be able to recycle anything. So you're printing a whole powder bed, all that powder that is supporting that material needs to be thrown away, right? You can't recycle it. Not once, not any time. And so that gives us very, very poor economics on if you're trying to make an implant or something like that in these kind of, and that's really kept this market very small to the most critical aircraft parts, to the most critical implants in the body. And are you able to change those economics with the PK material?
Yeah, so our PK 5000 will have stable physical properties and build conditions at a 40% virgin content refresh rate for powder bed fusion processes. If you are less worried about your physical properties, you can move down to the 30% if desired. But most of our customers care about physical properties, and that's why they started to look at polyketone in the first place. And the majority of our customers are using that 40% virgin content for the refresh.
So the economics are already like astoundingly much better than some of these materials, but some packs also have kind of some refresh and all this. Price wise, you don't have to disclose your price or anything, but we're assuming that this is also kind of more affordable than your standard Peak or PAEK, like the Peak family grades, right?
Yeah, absolutely. I mean, we're typically talking MSRPs in the $70 a kg range for this type of material, which is on par with many of the PA12s that you're going to be out there today. And of course, as with any user, the higher the volume that you utilize, the better the pricing gets.
That's really cool. And sometimes, like your Peak or something, that could be several times that much to buy. And then, of course, that refresh really affects that. It would actually probably drive that actual price much, much higher, of course, because you can't recycle any of it, or you can recycle very little of it.
Yeah, I mean, for the comparable chemical resistance, we're 5 to 7 times less expensive than a Peak or a PEC type product that you would typically find.
Okay, yeah, that's really cool. And then also at the same, do you have that inherent flame retardancy as well that the other Peaks have?
No, you get that from that aromatic portion. So these are not inherently flame retardant. We are working on some flame retardant grades, but it's not inherently flame retardant like the aromatics are.
Okay. All right. I was just curious. I didn't know that actually. And okay, so where do you see this being used? I mean, what are the most applications? I know that the Brenda's a Happy Bunny doing all sorts of cool stuff about that. I think Brenda will talk about that later. But what kind of applications are people using this material?
Yeah, I'd say that our biggest use cases are high damage tolerance parts. So think of things that need to take a very big jolt or have heavy repeated stresses that are going on in these parts. We have customers in the sporting goods industry using these on in-game prototypes. We have quite a bit of use cases in the barrier resistance area. So it has very good fuel barrier properties compared to polyamides and even PVDF materials. It has superior barrier resistance or lower barrier properties to enable your fluids to stay within the parts that you're designing. So things like fuel tanks, things like that. We've also seen a lot of interest in chemical handling and water connecting applications where customers are utilizing these to either carry high pressure water or to carry chemicals into mixing stations to consolidate traditional, what would have been a manifold assembly that would be stainless steel welded or PVC welded type structures. They're moving to a single manifold type structure out of this type of system. And another interesting area is wear properties. We have some users utilizing these in their material handling and warehousing facilities where parts need to see a lot of wear, and the polyketone product has very similar wear and lubricious properties to a POM or acetyl type materials. So it's a really diverse materials property set that allows it to be utilized in a lot of diverse applications.
And I like that chemical resistance, that pressure stuff. That's kind of stuff where you often see like PVDF, those types of materials. Is that also something you're seeing people replace polyvinyl? I always say that wrong. Polyvinyl dilene fluoride, PVDF. Oh, shit, PVDF. Are you seeing that kind of, because that's one of these kind of poor man's ultem kind of materials that you see a lot in kind of industrial materials in the chemical resistance, pressure resistance, use inside kind of heated areas of machines and cars and that. Are you a competitor to that as well?
Yeah, so we're looking at some rotomolded replacement applications that utilize PVDF today, and PVDF in general. There's some applications, or I should say, some legislation going on in certain areas to remove PFAs from the polymer chain. So the fluoropolymers are generally getting looked at replacement. So I say we're getting good looks at those fuel barrier applications that have historically been a rotomolded or two-part assembly that's got PVDF and some other materials for overall strength of the part. You can make those out of a monolithic polyketone material rather than making it out of a two-part mold.
Okay, yeah, that could be really cool. That's actually potentially really huge. But then explain to us, like, okay, so you've got this material that's kind of accessible and cheap and relatively easy to use and has better economics than all these materials. How did this come about? Because this is a really crazy story, actually, right?
Yeah, I mean, polyketone. We were at the Materials Innovation Center at Jabil. That's actually where Loomis Polymers was founded from. So Jabil recently divested its centralized additive manufacturing and engineered materials functions, including the related services and patents to the Loomis Polymers company, to allow us to really better serve our respective customers and our strategic focus areas. So Loomis Polymers is focusing on driving the innovation that was created at Jabil into the market and really growing this additive manufacturing space for materials for Loomis Polymers. And the Innovation Center at Jabil was a great area to really look at not just iterative changes to materials, but trying to find something that would really open up the application spaces for additive manufacturing, including, of course, keeping the economics of parts that go to scale in mind to make sure that this is something that can drive to high volume applications and really move additive manufacturing into larger spaces. So it was developed at the Materials Innovation Center at Jabil, and Loomis is continuing to drive innovations in additive manufacturing and continuing to drive that application space for this polyketone through partnerships and through our channels.
And one question, like, why don't you have a filament for this? Because this would seem really amazing as well. Does it not work well in FDM? What's the reason for not having a filament for this?
Yeah, it's one of those things that would work well. I mean, I worked a long time in filament, so I was the manager of materials research development at Stratasys. I've spent 7 years at Stratasys and developed many of the materials at Stratasys. And Polyketones are one of those materials where it would really, really benefit from a Fortis style printer, and due to the oven temperatures and the crystallization kinetics that are required to print good parts in all axes, as in not only dimensional stability but good physical properties in all axes. And we've really focused on, in general, the maker market and the light industrial markets, whether that's MakerBot style printers or bamboo style printers. That's really where we've focused our developments at, because of the much larger user base for those types of materials and systems.
Because at the moment you can print this on a bamboo, I want to spool this, right?
Yeah, and then you will get different physical properties out of powder bed fusion material than you do out of an FDM system. So yeah, we can put it on and we have made filament. We put it on smaller printers, but the physical properties aren't exactly amazing out of a polyketone product out of an FDM system. The anisotropy of it is very, very poor. So it's not something that we've moved forward with yet. We're working on it and working on modifying the polyketones to perform better in FDM systems or FFF systems, but it's not something that we currently have today.
And so it's difficult. I'm trying to convey the enthusiasm for this, because I am completely amazed by this material, right? And we've just haven't, and it's difficult, I think, for people to really understand that we just haven't had anything that has this exact kind of performance price kind of balance. And to me, it really is a huge thing for kind of like hard-wearing materials in the real world. This is actually a huge thing. And PK, for us, like, Brent and I are both like mega excited about it. So, just conveying the excitement, I think, is very, very difficult.
It is difficult, and it's one of the things I started with. It's hard to show in a data sheet. So when people just look at the data sheet, it's hard to understand resilience and what those physical properties mean. But when we go to shows and people get their hands on a part, they know immediately that the material is different, and it really is an aha moment every time somebody takes the time to pick up one of these polyketone parts.
Yeah, and I think for like the prosthetic and orthotic industry, this is where things get interesting, because many of the other times, and I've got plenty of PA12 sockets out there, PA11 sockets. I've got no polypropylene stuff out there. But the one thing that I've been waiting for, really, for the prosthetic and orthotic side of things, is a safety factor. So we know that the polyamides, when they fail, they do fail catastrophically. And even though the failure rate is low, it's still a catastrophic failure. And so one of the things that I think is important, and I saw this being described in a paper, is the being able to get home sort of thing. So like if you have a socket that fails, and it fails catastrophically, you can't use it to get home. The failure mode, and maybe Luke can speak a little bit more to this, of polyketone is not a complete catastrophic failure. It ends up being more like a tear. Not only that aspect, but then there's also the aspect of, with the polyamides and the PA11 and PA12, and we've had Jimmy on, Joris, where you have the adjustability, but to have the adjustability, you have to cut massive parts of the socket away. Well, when you do that with a polyamide, you also start introducing weakness or stress risers. But when you do it with PK5000, you can actually be way thinner. You can open these sockets up more, which then allows you to take full advantage of additive manufacturing for prosthetics and orthotics. So it's no longer, hey, we're just 3D printing a prosthesis. It's like, hey, we're 3D printing a prosthesis, and it's something that we cannot do in traditional fabrication, and it looks good. And we're taking advantage of all the properties of the material. So that's to me, that's what's exciting about the prosthetic side of things. But there's a whole side, and we don't talk about this enough on the show, on the orthotic side of things, where you have the ankle foot orthoses and knee ankle foot orthoses, where that population is much greater. And one of the ways that our field has typically created orthoses and prostheses is either through some sort of thermoplastic polypropylene or composites, so pre-preg composites or even wet laminations. But those, especially when they're stressed, they're very strong, but when they're stressed, they do fail. They'll crack in specific areas. And I feel like the polyketone, at least from what we've seen specifically in the dynamic AFO side of things, is definitely going to last much longer, and the failure mode is different. So, I think there's a whole exciting part about the prosthetic and orthotic, or the prosthetic side, but there's even more of an excitement on the orthotic side of things, because the orthotic side is always a little bit lagging on the technology, but now I think we have something that's very, very special. So those are some of the things that get me excited about the material.
It's a great material for that use case. Between the resilience and the recoverable work, the parts are going to last longer in those types of use cases.
And do you feel like, and how are you guys going to commercialize this at the moment? Can I just buy this stuff if I want to? If I want to buy it, how do I get it on which machine?
Yeah, so it's available to buy direct from Lewis Polymers. Typically, we can help you with material system integration depending on what platform you're utilizing. So if it's a Farsoon platform, we have those data sets for every type of Farsoon platform that is out there. Those are easily transferable to older DTM systems or some of the older 3D systems. And if you have a newer 3D system or a newer EOS system, you can work with those suppliers to get that material integrated on your platform.
And do you think, if I want to get if I'm like a prosthetics person, I'm like, okay, wait, how do I get involved with this material? Can I order parts from it? Can I get people to design for it? How does that work?
Yeah, absolutely. So Brent recently has a machine. So Brent is one person that you can go in and get parts from. The overall industry is getting ready to start making parts for customers pretty broadly, and there's a couple of people that are ahead of getting that material onto their platforms.
And then we can design. So, I mean, it's almost going. It's hard to believe going on a year. So Luke tried to get me to try this material back in 2019. And that was just when I was starting. And I had my hands full with just trying to figure out which way was up on the design side of things. Well, 3-4 years later, we've connected, but we've been designing for this stuff and really trying to push the envelope of what is possible for really about the last year or so. So we're always willing to help design. And then we, if we're not able to print it on our machine, we also have some great pricing because of our connections or relationship with some of these contract manufacturers that allow us to purchase essentially builds. And so we're able to really bring down the costs. Like most of the time, that's one of the things that I've figured out in the contract manufacturing world is that it's not only just material costs, but it's how long does it take me to get your product onto my machine? And so if you reduce that friction and you take up a whole build volume, you're going to get the economics of that makes more sense than me trying to squeak one part into somebody's machine. Those prices are going to be way more expensive. And so that's one of the things that us at Advanced 3D we try to do is leverage, hey, we're already going to be running. You can put that part into our build and it's going to be more cost effective for you to do that.
Okay, this is super cool. I hope we've tried to get people to understand why this is so amazing that we can get something. It's kind of like, it's kind of like there's lots of cars, but then there's a Model T kind of thing. You know what I mean? Is the Model T different than the other cars? Well, no, but yes, at the same time, it's completely different, right? So it's not. It has the right combination of flavors and things, though, so that all of a sudden, you could have a real performance and price kind of breakthrough. And I think that could be really exciting using this in hardware applications for perhaps a lot of different parts on prosthetics and orthotics and stuff like that. So I'm super excited with that, and I hope we managed to convey that today, gentlemen. So thank you so much for being here today, Luke.
Thank you for having me. It was great.
And thanks a lot, Brent. Yeah, reach out to either Luke or Brent if you want to try out PK5000 and try out, see if this will work for your business. And we can't wait to find out what this results in and what happens because of this. Because this is really, really, really cool. So thank you so much for listening to another episode of the Prosthetics and Orthotics podcast.